Hello, everyone, and welcome to our first lecture of the semester. This course is about GPU computing, as you all know, and today I'm going to be giving kind of an introduction and a motivation for why GPU computing emerged and what is GPU computing. Next time, hopefully, we'll get started with the kind of learning about GPUs and writing GPU programs and things like that. Okay, let's get started. And to start off, I want to talk a little bit about the history of how computers or computer technology has evolved over the past half a century. We have a lot of ECE students here, and then also I know the computer science students should also be familiar with this. So how many of you here know or remember what Moore's law is?
Transistor density doubles every year. It was every year, but then changed to every 2 years. But now it's reaching its end, yani.
Right, exactly. So Moore's law, it's not really a law. The physics people with us probably cringe when they hear us calling it a law. It's not really a law. It's more of a prediction. So it's a prediction that was made by Gordon Moore, who was one of the co-founders of Intel. And what Gordon Moore predicted is that, and he made this prediction, early on, he predicted that the number of transistors per unit area would double every 18 to 24 months. Okay, this was his prediction. He certainly did not intend for his prediction to last as long as it did, but it was kind of a self-fulfilling prophecy, and semiconductor companies started putting this as their target. And so it was that over the past half a century, we've seen that the number of transistors per unit area has indeed been doubling every 18 to 24 months. Now, as one of your colleagues has pointed out, this trend is coming to an end because we are kind of coming close. These transistor devices are getting smaller and smaller, so they're getting to a point where they're just too small for us to be able to make them any smaller. Nevertheless, because the transistors, the number of transistors have been doubling, the number of transistors we can fit per unit area has been doubling every 18 to 24 months. When these transistors get smaller, it actually becomes easier and easier to switch them on and off faster. And because it's easier to switch them on and off faster, what that means is we can increase the clock frequency in our processors faster. And that is why the processor frequency followed a similar trend, where the frequency at which we were able to drive our processors also doubled every 18 to 24 months. And that continued up until 2005. So in 2005, we kept on getting more and more transistors per unit area. The transistors kept on getting smaller and smaller, but we could no longer switch them on and off, or we stopped switching them on and off faster. We stopped doubling our frequency every 18 to 24 months. Anybody knows why?
Isn't it because of the power wall limitation, something like that?
Right, exactly. It was because of power. So when you switch transistors on and off faster, you're going to burn more power. And what's the problem with burning more power?
Generates heat.
Generates heat, right, exactly. And what's the problem with heat?
It melts the CPU.
Exactly. The problem with heat is that if you don't cool it, it melts the CPU. So what happened was that the reason that the frequency stagnated is because the CPUs got so hot that we could no longer, our cooling technology was unable to cool them if we went beyond this. So around 2005, what happened is we kept on getting more and more transistors on the chip, but we could no longer switch these transistors on and off faster. So before 2005, if you bought a computer, you wrote a program to run on that computer. If you buy another computer 2 years later, that program is twice as fast. without you having to do anything, because the frequency was twice as fast. But after 2005, simply running the same program on a newer computer, you no longer gave you twice the speed up. Now, we still were getting a little bit more speed up, so the single thread performance did not completely stagnate like the frequency did. It did increase, it did keep increasing, it just didn't increase at the rate that it was increasing before. And the reason the single thread performance kept on increasing is for two reasons. The first reason is compiler advancements. So compiler technology became more and more advanced, and compilers were becoming better and better at optimizing code. But another reason is all these extra transistors that we were getting, right? So these extra transistors that we were getting, even though we switched them faster, the fact that we had more transistors meant we could afford to do more and more sophisticated hardware techniques to get our threads to execute faster. And those of you who have taken advanced computer architecture courses are probably familiar with some of these techniques, all of these different speculative execution techniques like branch prediction, out of order execution, etc. Okay, so we kept on getting single thread performance, but it wasn't that increase was no longer as dramatic as it was before. Because of this stagnation in single thread performance, we were getting more transistors, but we were not getting that much better performance. So what did people start doing with these transistors? These more transistors that we were getting, that we cannot switch faster. Right, exactly. So around this time when we had the stagnation in frequency, this is where we saw an explosion in the number of cores on chip. So this is where processors, or mainstream processors, of course we had parallel processors before this, but mainstream parallel processors, this is the point where they switched from being single core processors, where you just have one core in your processor, or like one data path that's executing instructions, to a large number of cores. So this was the explosion of parallel computing. Stagnation in single thread performance made parallel computing mainstream. And hardware designers started investing more cores into their processors. And obviously, the software follows the hardware. So when hardware folks said, hey, the only way we can give you better performance is by giving you more cores, the software people said, well, the only way we're going to get more performance is we have to go and rewrite our program so they can run in parallel. So the free lunch was over. You could no longer get free performance by simply rerunning the same code on a CPU 2 years later. You had to now go and rewrite your code so that it runs in parallel. Okay, any questions so far? All right, great. So let's look at various design approaches for designing systems in general. If I want to design a system that accomplishes some task, or maybe accomplishes many tasks, in general, there's two different kinds of design approaches. There's latency-oriented design, and there is throughput-oriented design. And this is not just in computer systems, by the way. This is in any kind of system that I would like to build to accomplish some task. So an example of latency-oriented design is a car. Okay, a car, for example, is designed to take you from one place to another place, in a fast amount of time. And if you compare that with a bus is designed to take more people from one place to another, but every individual person gets there in less amount of time. So if you compare a car to a bus, a car would be an example of a latency-oriented design where I am minimizing the time it takes to perform a single task. Whereas in throughput-oriented designs, a bus is an example where you are maximizing the number of tasks that you can perform in a given time frame, even though each individual one of those tasks is going to take more time, right? So if I want to take one person from point A to point B, I'll probably use a car. If I want to take 2 people, I'll probably still use a car. If I want to take 4 people from point A to point B, I'll probably also use a car. But if I want to take 20 people from point A to point B, that is where the bus starts looking like an attractive solution. Because if a car wants to take 20 people, it's going to have to make multiple trips, whereas the bus can take all those people in a single step. Okay? So someone is asking, why didn't they innovate the cooling technologies? So to be fair to our folks who work on cooling technologies, there are a lot of innovations that happen in cooling technologies. It's just a matter of the physics, right? At some point, it just becomes really, really hard to cool these things. I mean, when the heat of your chip is as hot as the surface of the sun, cooling technologies start to not be so good at dealing with that. Okay, I'm not saying they are, but if we kept on doubling our frequency more and more, we would not be too far away from getting there. Okay, so some things are just they're just not within our physical capacity. I mean, cost issues, of course, right? So obviously, if you were willing to spend $1 million to cool your chip, then you can probably double your frequency more and more. But most people don't want to spend that much money on cooling their chip. Okay, so back to latency-oriented design and throughput-oriented design. So in the same way that we can design vehicles in a latency-oriented way or a throughput-oriented way, the same thing applies to processor. So the approaches to processor design are similar in this way. A CPU is an example of a latency-oriented design, and a GPU is an example of a throughput-oriented design. Okay. In other words, if I wanted to accomplish one task and as fast as possible, I'll probably use a CPU for that, not a GPU. But if I want to accomplish many little tasks within a certain time frame, that is where the GPU becomes an attractive solution. And let's see how these two different design approaches impact how CPUs are designed and how GPUs are designed. So there's different components of a processor. A processor has the ALUs, for example, that are responsible for doing a whole bunch of math. A processor has control logic that orchestrates the execution of different instructions, and a processor obviously has caches. So cache on chip so that you can you keep the frequently used data on chip close to you so that you can access it frequently. So one example of how CPUs are latency oriented versus GPUs are throughput oriented, a CPU typically has a few very powerful ALUs. So these ALUs take up a lot of space because they're highly optimized to reduce the latency of a single operation, right? We design the ALUs in a CPU such that the add operation is as fast as possible, or even the multiply operation is as fast as possible. Those of you who have taken a computer architecture course, you've probably seen the difference between an n-bit multiplier that takes n cycles versus an n-bit multiplier that can be done in one cycle, but uses much, much more hardware. So ALUs in the CPU are very powerful. We invest a lot of area in these ALUs in order for us to reduce the latency of every arithmetic operation as much as we can. In contrast, in GPUs, our ALUs are much smaller, they're much weaker, they take much longer to perform one operation. However, we have many of them. Okay, we have many of these ALUs, but each of them takes much longer to perform the same operation. Because of that, one thing we can do is we can pipeline these ALUs to improve the throughput of them. Those of you who have taken a computer architecture course, which I think most of you have, are familiar with how pipelining improves throughput, even though it's at the expense of latency. So by having these small ALUs and pipelining them, we can have very high throughput of arithmetic. However, each individual operation has much longer latency. Okay. Another example is caches. So in CPUs, we have large caches. Why do we have large caches? Well, we have large caches because we want to convert our long latency memory accesses that go to DRAM. We want to convert them into short latency cache accesses. So by making our CPUs larger, we can reduce the miss rate. By making our CPU caches larger, we can reduce the miss rate in our CPU, and that allows us to have shorter and shortened latency memory operation. In contrast, in the GPU, we actually have smaller caches, and what that means is that we are more likely to we are less likely to hit the cache and more likely to have to go to memory to access data. However, the advantage of having smaller caches is that we can dedicate more area to compute. We can have more of our silicon dedicated to ALUs instead of having caches, and then we can and because of that, our memory access operations are going to take a longer time, but you'll see how we're going to deal with that to tolerate that latency. Similarly, with control and CPUs, we do all kinds of magic in order for us to speed up our control. So branch prediction to reduce the control hazards, data forwarding to reduce data hazards. We also do crazy things like out-of-order execution in order for us to improve the latency of a single thread on a CPU or a single task on a CPU. But all of that is expensive, right? To do branch prediction, you need to have all this hardware branch prediction. To do forwarding in the pipeline, you need to have all this hardware for hazard detection and the forwarding unit. And to do out-of-order execution, you need all this additional hardware to do it, right? So all of this takes up a lot of area on the CPU to reduce. In contrast, a GPU, we're going to have our operations are going to take longer. Our branches will take longer. Our data hazards, we're going to have to live with them, right? You might have some forwarding, maybe not. Okay, but all of this, you're going to pay all this latency price in order for you to have more throughput. Okay. Any questions so far? Is computer architecture fresh in your memory, or is it taking time for all of it to come back?
I need some time to remember these things.
Okay. Well, we're going to be talking a lot about this throughout the course. So hopefully, if you're not following with me 100%, I think that's okay. You'll be able to kind of pick up on things quickly. Okay, so let's talk more about latency versus throughput. So in CPUs, because operations don't have high latency, we still have stalls in our pipeline, but we don't have that many. Okay, relative to the GPU, for example. So on the CPU, what do people do on the CPU in order for them to hide stalls in your pipeline?
Scheduling.
Sorry?
Scheduling. They schedule instructions in a way to help these latencies.
Okay, so you can do all kinds of fancy compiler techniques to schedule your instructions to minimize, the stalls. But once the software has done its part, once the compiler has done its part, and the hardware is executing, what can the hardware do to minimize the number of empty cycles that you have? What does hardware do nowadays in CPUs?
Out of order or ROB وهيك.
Right, you have out of order, ROB, exactly, deep pipelines. But then there's also, and I'm sure you guys are familiar with this, there's also multi-threading. Right, there's also multi-threading. So those of you who have learned about superscalers, so multi-threading is one way to hide latency. So you use the same core to execute multiple threads. And that way you have two different threads executing at the same time. So if there's no instruction from this thread ready to execute, you'll find an instruction from another thread ready to execute. So by bringing in instructions from multiple threads, from multiple threads. This is called multi-threading. You're able to use the stall cycles of one thread to execute instructions from another thread, and vice versa. So on CPUs, we have a modest amount of multi-threading to hide latencies, to fill these stalls, or to make sure that our pipeline doesn't have any bubbles, any empty cycles. What's a typical number of threads that you would execute per core on the CPU?
2.
4?
4. It's more typical. 2 is more typical. So 2 is more typical, because CPUs are already designed to not leave many cycles open. So a typical number of threads that you would execute at the same time on the CPU. So I'm talking about simultaneous multi-threading or hyper-threading for those of you who are familiar with Intel. A typical CPU would have 2 threads running at the same time on the same core in order for you to be able to have access to 2 different instruction streams, so that if one thread if you don't have any instructions available from one thread to fill your pipeline, you can get instructions from another thread.
Professor?
Okay, so yes.
When you say that, it's 2 threads per core, right?
Yes, 2 threads per core.
Okay.
Yes, that's what I mean. 2 threads per core. If you have an 8-core CPU, you're going to have 16 hardware threads. Okay, 2 threads in every core. Yes, thank you for that point. Okay, so you have a modest amount of multi-threading in order to hide the short latencies. Now, what do you expect for there to be on GPUs? In GPU, if I have these long latency operations, right, that means I'm expecting to have a lot of bubbles in my pipeline. So what do you expect I'm going to do on the GPU?
Increase the number of threads per core.
Right, exactly. So on GPU, I'm going to have a massive number of threads to hide the very high latency. And by massive number of threads, I don't just mean the fact that I have many more cores, and therefore I have many more threads because I have the same number of threads per core. Not only am I going to have many more cores, but I'm also going to have many more threads that are scheduled on the same core in order for me to hide these high latencies. So because my ALUs take a long time, and because my memory accesses take a long time, and because my control decisions take a long time, in order for me to avoid having to wait for all these operations to finish and stall my pipelines, I'm going to have many more threads that can execute on the same core at the same time. That way, instead of having a selection of, instead of being able to select between 2 different threads, if I have an empty cycle that I want to fill, I can select maybe between 32 or 64 different instruction streams. Okay, so this is another example of the difference between latency-oriented design and throughput-oriented design. And then finally, CPUs have high clock frequency and GPUs have moderate clock frequency. So GPUs are usually clocked at lower frequencies than CPUs because GPUs already consume more power. So in order for us to be able to fit all this stuff on the GPU and run it, we need to clock it at a lower frequency. Okay, any questions?
Professor, one thing that I don't understand is if we're able to manufacture, for example, ALUs that are very performant, why wouldn't you want to put them in your GPU?
Well, because they take up more area. So one CPU ALU takes up as much area as multiple GPU ALUs.
Okay, I see. Thank you.
So the difference is between, so you can either have a large ALU where you reduce the operation latency, or you can have many small ones so that you can have higher throughput. Okay?
Doctor?
Yes.
In GPUs, do we call the threads tasks? Well, when do we call tasks? When do we say threads?
So I'm using the word task here because I haven't really introduced what a thread is on GPU. GPUs, you have threads, you have warps, you have blocks, you have grids. So there's different notions of workers working in parallel. So that's why I've been using the word task somehow. But we definitely have threads on CPUs and we have threads on GPUs, we'll talk later about when we say thread on a GPU what we mean.
Okay.
Okay. Okay, so having kind of gone through all this computer architecture stuff, let's go back and talk a little bit more about the history. So where did GPUs come from? So GPUs were originally built for graphics, and that's where the name comes from. A GPU is a graphics processing unit. Okay, and it was built originally for graphics. And the unique thing about graphics workloads is that they are massively parallel. So when a GPU, when you're kind of doing these you're computing these graphics workloads, you usually have to process a massive number of pixels in parallel, and a lot of times these pixels are kind of independent from each other. So you can that's why the GPU as an architecture is designed to have this massive parallelism and have this throughput, right? You care more, with a GPU, you care more about, you don't care about one pixel being rendered as fast as possible. You care about having your thousands of pixels on your screen all appearing within a certain frame rate. So this is kind of the motivation for why GPUs have this throughput-oriented design and where GPUs came from. Now, what happened later on is before people realized that these GPUs, even though they were built for graphics, they were actually useful for doing other kinds of computations where you also cared about throughput. And this started this trend towards general purpose GPU computing. Now, when people realized this, before 2007, the only way for you to program GPU was using these graphics APIs that the GPU vendors gave you. And these are things like OpenGL, Direct3D, for those of you who are familiar with graphics. So people who wanted to do general purpose computing on GPUs, what they had to do is they had to somehow reformulate their computation in terms of functions that paint pixels. So they had to take this computation that had nothing to do with graphics and then reformulate it as something that operates on pixels in order for them to use these APIs to leverage the GPUs to perform their general purpose computation. Now, when these GPU companies found that people were doing this, what NVIDIA did, and NVIDIA was kind of the pioneer. NVIDIA is a major GPU vendor. AMD also produced GPUs. You have other companies that produce GPUs, but NVIDIA is by far the biggest. So in 2007, what NVIDIA did is it released CUDA, and CUDA was essentially a programming platform for using GPUs in a general purpose way. So you had now this interface where rather than calling these graphics functions to program the GPU, you could simply write a general purpose program that ran on the GPU. And of course, it wasn't just about creating a new interface. This new interface also required extensions to the GPU architecture. So there was quite a bit of work involved in converting this GPU to a processor that can really run a general purpose workload, and that's exactly what NVIDIA did in 2007. And this switch in 2007 is what marked the beginning of the GPU computing era, where more and more people started moving towards running their applications on GPUs in order for them to get high performance. This over here is a image that I pulled from Jensen Huang, is the CEO of NVIDIA. He's also the co-founder, and this is from his keynote speech at the GPU Technology Conference in 2015. And this kind of shows you between 2008, which is the year after CUDA was released, and 2015, how much there was change, an increase in GPU computing. This here is the number of people who downloaded CUDA from 150,000 in 2008 to 3 million by 2015. Applications that use CUDA, university courses that were teaching CUDA, for research papers that were published related to GPU computing. The number of GPUs that were used for non-graphics workloads, so high-performance computing workloads, and this over here is the number of teraflops or terafloating point operations per second that GPU computing was delivering to the community. So from 77 supercomputing teraflops to 54,000 supercomputing teraflops, and this is just 20, right? By now it's much higher, but unfortunately I wasn't able to find a graph that gave these trends up until 2020. This over here I pulled from the keynote speech in 2019, and this also shows you the trend more recently from 2018 to 2019. So you had 800,000 developers who were developing in CUDA, and then 1 year later you had 1.2 million developers who were developing in CUDA. And a very important trend over here that influenced this was the increased adoption of GPUs for machine learning. And you know, there's a whole history behind that I won't get into, but we are still continuing to see this huge move towards adopting GPUs for people to run their applications on. And here you had 8 million CUDA downloads in 2018 versus 13 million CUDA downloads in 2019. Okay, if we look at the top supercomputers in the world today, you'll notice that many of them are also running GPUs. So here there's a website called Top 500 that tracks the top 500 supercomputers in the world. And they publish their data, I think, every 4 months or so. So this data is from November 2020, which is the most recent list that was published. So the GPU accelerated computers in 2020, the #1 computer in the United States, which is the #2 worldwide, is called Summit. This computer uses GPUs as accelerators. The #1 supercomputer in Europe called Joules. This is in Germany. It's also the #7 worldwide. This uses GPUs. The #1 computer in the Middle East is also a GPU accelerated supercomputer, and it's also the #10 worldwide. It's called the MAM7. This is actually hosted by Saudi Aramco. 6 out of the top 10 supercomputers in the world are GPU-equipped supercomputers. Summit actually used to be #1, but this year, or in 2020, there's a supercomputer in Japan actually that became #1 that's not using GPUs. But nevertheless, you have 6 out of the top 10 supercomputers in the world using GPUs. Also, interestingly, is that the #1 computer in the world in terms of energy efficiency is GPU equipped, and this top 500 list includes another list, which is the Green 500, and these are the energy efficient supercomputers. And 7 out of the top 10 energy efficient supercomputers are also GPU equipped. Why do you think GPUs actually have higher power than CPUs? Those of you who are might be into gaming, you know that if you have a fancy GPU, you need to get this special power supply to power it. So GPUs have consume more power than CPUs. So why do you think they would be more energy efficient if they consume more power?
Well, if you take, for example, a typical one has maybe 128 cores. So divide each core by the power by the number of cores, and it's going to give you much more energy efficiency, I guess.
Okay, I think I know what you're getting at. So the key idea here is that we're talking about energy, right? So if you consume more power, if you consume maybe 1.5 times as much power, but you finish 10 times faster, right? Then overall, you're going to reduce the total amount of energy you spend, because energy is a function of both power and time. So consuming 1.5 times more power to finish 10 times faster is actually worth it if you care about energy. If you just care about power and you don't care about energy, that's a different story. And this is why this doesn't say power efficient supercomputers. This says energy efficient supercomputers. Ultimately, energy is really your bottom line, because energy is what impacts the bill that you get at the end of the month from the energy company. Okay, and of course, more importantly, how much carbon you're releasing into the environment. Okay, so why GPUs? There's all kinds of ways you can build a parallel processor. Why did GPUs in particular succeed? Well, those of you who are familiar with chip design, you probably know that chips are very expensive to build. They require a lot of engineers. They require a lot of prototyping, a lot of testing. The fabrication of a chip has a very high fixed cost. So chips are very expensive to build, and in order for you to be able, they have very high fixed cost, and in order for you to be able to amortize this cost, you need to have a very large volume of sales. And because of this reason, the market of chips is actually very difficult to penetrate. It's very difficult for you to come up with a new CPU or a new GPU and penetrate the market, just because the fixed cost is so high. So in order to be able to go on this endeavor, you need to have this guarantee that you're going to have a very large customer base ready to purchase this chip. So when parallel computing became mainstream, GPUs already had a head start because they already had a large customer base from the gaming sector, right? So and because GPUs had this head start, so they had a head start compared to other potential massively parallel accelerators. So when the switch to parallel computing happened, you could have imagined that some company would come and design this chip that was designed specifically for making scientific applications run as fast as possible in parallel, and it was designed to be this parallel processor for scientific applications that was highly customized to those. The problem with that is that it would have a small customer base, whereas GPUs already had this huge customer base from the gaming sector. So when this switch towards parallel computing for general purpose applications happened, it was easier for a company that was already manufacturing GPUs to kind of adapt their GPUs to accommodate general purpose workloads, as opposed to some new company coming and building a customized, or not a customized, but a new parallel architecture that's designed for general purpose workloads. And this is what made GPUs really able to become mainstream. If you look at the market sector breakdown for GPUs, you have 58%, and this is from 2019. You have 58% for gaming, 24% for data center, 9% for professional visualization. This is things like if you have movies, you're trying to render movies and things like that. Automotive 5%, and then other 4%. Okay, and then data center itself is broken down into enterprise solutions, hyperscale, and scientific computing. So this scientific computing part is where a lot of the folks in physics or geology, bioinformatics, nuclear engineering do all their simulations. So if you were to come and design a chip for just this market sector, for example, you're not going to have the volume of sales to amortize your cost that GPUs have, because GPUs still get the majority of their revenue from gaming. Okay. Another thing to keep in mind is that because the GPU has all these different target markets, oftentimes when GPU companies come and make decisions about how they're going to design the GPU, how they're going to what architecture improvements they're going to make, it's not enough for them to benefit one of these markets. They need to make sure they don't hurt another market. And this is an issue with a lot of research, for example, that comes out related to GPUs. So you have a lot of research sometimes that comes and says, hey, if we just make this small architecture improvement, it will improve the performance of scientific applications by this much. But then if you go to NVIDIA and say, hey, why don't you make this improvement to your architecture? Well, they'll tell you, if this improvement is going to hurt our performance in gaming, then we're not going to do it, because gaming is our biggest customer base. So if something will improve the performance of scientific applications but hurt at the expense of the performance of our gaming workloads, then forget it. We're not going to invest in it. Okay. So this is just some of the history behind GPU computing, some of the reasons why GPU computing took off, and some of the considerations that technical and also business considerations that go into how we design GPUs. Now, in this course, we're not going to be focusing on gaming. We're not going to be focusing on graphics workloads. We're not going to be focusing on professional visualization. We're not going to be focusing on a lot of these things. We're actually going to be focusing on how we can program GPUs in a general purpose way. And a lot of the examples we're going to look at are from scientific computing, and they're going to come from this data center segment of the market. How to take this GPU and program it so that we can make our physics simulations faster. How to take it to program it so that we can make our deep learning workloads faster, etc. Okay. Any questions? All right. So yes, do you have a question?
Yes, I was just concerned that the deep learning and the machine learning, where does it fall in these scales?
It falls under data center.
All right. Thank you.
Okay, so at the end of every lecture, first of all, the textbook that we'll be using in the course is this book over here, Programming Massively Parallel Processors, A Hands-On Approach by David Kirk and Wenmei Hu. And at the end of every lecture, what I'll try to do is I'll try to have a slide that tells you what sections in this textbook the lecture course corresponds to. Okay. So this is the slide that I'll have at the end of every lecture, so that you know where to look in the textbook if you would like to read more about the material covered. And I do encourage you to go and read more about the material in the textbook, because not every point made in the textbook I can cover in class. So there's a lot of additional things you can learn by reading the textbook. Of course, any material that you kind of need for the assignments, any material that you will need for an exam, for example, will be covered in the lecture. But there's a lot more to learn. It's a very rich textbook. So there's a lot more to learn when you read the sections in the textbook. Okay. And with that, I'm going to stop the recording here. And for the remaining part of the class, I'm going to go through some of the logistical aspects of this semester's offering of the course.